First, thank you very much for having me here. I'm Glauber Costa, live in Toronto, and I work for ScyllaDB as a principal architect. Together here with me, I have Mina Naguib. Is from AdGear, Samsung now, and he's one of our hopefully happy customers. And we'll talk a little bit about what ScyllaDB is. So what ScyllaDB is, we will get there. Why do we exist? What do we provide? What's the story about this database? Maybe some of you have heard about us, maybe you didn't, you do now. And then Mina's going to talk a little bit about their deployment, their story with ScyllaDB, and after that, I hope to tell you a little bit more about how we do the things that we do. On the plushie, the story is like we didn't bring t-shirts, but that's on purpose. If you tweet pictures of you and your plushie and tag us, that's at ScyllaDB on Twitter, close to a landmark, because we have this campaign now, ScyllaDB around the world. Toronto is taken, I've already took the picture there. But if you go to some place that is famous and anywhere and say, hey, I'm here and I'm around the world with ScyllaDB, tweet it, we'll potentially ship you a t-shirt, unless your picture is really bad. Mention us, keep in touch, and that's the story. So you please, unless we run out of them, get a plushie, don't be shy. So what we're going to talk today, as I said, first, very quick primer about what's ScyllaDB. Why are we here, and what do we do? Why do we do the things that we do? And then how that story helped AdGear, now Samsung Ads, that's correct, right? Samsung Ads here now. How we're helping them do the things that they do. And then I'll tell you more about the how. So just the first question, who here have heard before about ScyllaDB? Oh, that's much better than last year. Last year was like, oh yeah, 1, 2. For those who haven't heard about ScyllaDB, have you ever heard about Apache Cassandra? Yeah, but you heard about ScyllaDB as well. You don't count. All right, so yeah. How do we put this together? So when we look at the NoSQL landscape, right? When we're talking about the database that holds the data for you to do your data science, for you to do your big data, there isn't a clear winner yet. So we have DynamoDB, and now we have other solutions from the other cloud vendors. We have Google has a solution, Microsoft has Microsoft Cosmos. The cost of running those solutions is usually fairly high. We have studies published about that. Some of them, they're nice when you have a little bit of data, it very quickly explodes. And you also have lock-in. You can't really do, if you decide to go with Dynamo, you can't really do multi-cloud. How are you going to do multi-cloud with Dynamo? And then you have organizations today, they're coming from acquisitions, they're all in their different clouds. How do you integrate all that? You can't. And then you have MongoDB, which is also a big player. MongoDB usually faces problems with scaling. We've heard from a lot of customers, MongoDB is the easiest solution to get started. It got started in 15 minutes. Once it got past a certain threshold, it became hell on earth. Doesn't do multi-DC very well. It's a document store. If you're really after latency, is really not the thing for you. And then we have stuff like Redis, which is not really a database. They're trying now to become more of a database, but they've traditionally been doing a great job as a cache, but it's not clear yet if they can grow to become a database. And then you have Cassandra, right? We love Cassandra. When we look at Cassandra, what we see is that it has the right architecture. It scales extremely, extremely well. We've heard about other companies. I think Apple has a cluster of Cassandra with more than 1,000 nodes. So it's pretty impressive. So it's pretty proven technology. We know it's the best solution for high availability. But what are the problems with Cassandra? First of all, the price-performance ratio is not where we want it to be. The reason for that, Cassandra doesn't scale up very well. So you got to scale just out and out and out and out, and out of a sudden, not only you can have those clusters with 1,000 nodes, you pretty much have to. Then there's a lot of complexity. Tuning Cassandra, I've heard before, it takes 3 PhDs to manage. Super complex. I only have 2 masters. How am I supposed to manage Cassandra? And then there's the JVM. The JVM itself is the source of a lot of that complexity. How do I tune it? How do I pick the right garbage collection strategy? How do I do this? How do I do that? A lot of work goes into that. So we love Cassandra, but we see problems with that. And the summary of the problem is that Cassandra is a great database if you look from the top down, but it doesn't really do a great job from the bottom up. The Cassandra node is not very efficient. And then comes ScyllaDB. What we do at Scylla in our mission to be the best NoSQL database, to close this question once and for all, is that by following the Cassandra architecture, and we actually do a lot more than that, we are fully API compatible with Cassandra. We market ourselves as a drop-in replacement for Cassandra. All the tooling work that was written over the years to work with Cassandra works with Scylla just fine. If you talk to Scylla or Cassandra over CQL, that works. If you have a Thrift application, Cassandra actually deprecated Thrift anymore. We don't believe in deprecating stuff, so we're keeping that. So we're going to be able to keep using our Thrift applications like pretty much forever. The Spark connector that works with Cassandra works with Scylla. Kafka works with Cassandra, works with Scylla. So all the ecosystem that over the years were written to work with Cassandra just works with Scylla. Oh, I already know how to manage a Cassandra cluster. I'm very familiar with Node too and with things like that. All of that works. It's not just the language. When you look at Microsoft Cosmos, for instance, they're now providing into their database CQL language compatibility. But we go a step further because we follow the same architecture. We use the same concepts. We do multi-data center the same way. We do replication the same way. We do consistency level the same way per request, everything. Some people, some organizations we've seen, like they have separate DevOps and application teams. Sometimes the DevOps just switch the cluster, the application, they don't necessarily notice. They just notice, oh, my application is timing out less now. So we really try to be compatible to that level. All the good is with Cassandra, but we also provide more than 1 million operations per second per node. Are you going to get that with every workload? Of course not. They don't get it. Most people don't get it, but it's a real number. It's not just I made up and 1 million sounded nice. No, we actually can do that. We usually do that in our demos. It's not really a workload that is very challenging, but it's real.
Is it a million ops or a million forward?
We can do reads as well as writes, and that's something that I'll allude to. But most of the time we're demoing writes and etc. But we can do reads fairly well as well. I'll also get you that in details. Like Cassandra is usually not very good with reads. They focus more on writes. Like we can do both equally well. Usually, again, also depending on the workload, around 1 millisecond for the 99th percentile latency. For complex workloads, as you're going to see from them today, it's going to be higher than that, but it's not going to be a lot higher than that. And my favorite 2 bullet points. Scylla is auto-tuning. There's no tuning in Scylla. First, there's no JVM, and 40% of the whole Cassandra tuning thing is already just tuning the JVM. We are a native C++ application. We have nothing against Java per se, but we believe it's not really the right choice for the job when you're writing a database. So there's no tuning. I'm also going to expand on that. Like Cassandra, it's not just the JVM tuning that hurts you. It's also like how do I tune compactions, speeds, and etc. Number of writers and number of readers. All of that in Scylla is just automatic. And no, I'm not talking about good defaults. I'm talking dynamic algorithms that can do that for you. And also we scale up and out. Some of our users, we have plenty. We have one of them here today. There's going to talk more to you about their use case. But we also have brands like AppNexus, IBM, Zenly, and not all of them are here. OlaCab is actually an interesting one. It's like the Uber for India. They just published a couple of weeks ago a very nice use case using Scylla, describing how they're doing their mission-critical stuff with Scylla for more than a year now. CERN and a lot of others that you recognize, and hopefully in the future, maybe your brand here too. The folks that are not here either because they didn't fit in the slide or because they didn't authorize us to use the brand. That happens as well. So this is repeated? Yeah, no, it's just a... So very quick summary. So Cassandra, very good architecture. Like when you look from the outside, it really is the right way to do it, we believe. I mean, very flexible. You can choose your consistency. The database can do whatever you want it to do, but it can't really utilize the machine efficiently. The Cassandra node is not really efficient, and Scylla scales linear. I'm going to show you that today. The latency in Cassandra tends to be very high, especially when you get like garbage collection, you get pauses, you get stuff like that. And even if you overcome that problem somehow with all the tuning, it's still usually not where you want it to be. With Scylla, we have very low and very consistent latencies. That's the most important thing for us. If your latency is going to be 3 milliseconds, I want it to be 3 milliseconds. I don't want to be 3 milliseconds now, 5 milliseconds later, 25 milliseconds tomorrow. It's got to be, for the same workloads, it's got to be consistent. And also, complexity. Cassandra is a fairly complex beast to tame. Scylla is all auto-tuned with dynamic scheduling all the way. But admin is about the same. So part of the auto-tuning we do is that when you do maintenance in the cluster, the maintenance operations, they don't disrupt the workload as much. So in Cassandra, if you're going to do a repair, usually, oh my God, I got to schedule this very well, because if I run the repair at the same time a load is coming, all I can do is pray for the best. But with Scylla, we try to make guarantees about your SLA regardless of what's going on. Before I hand it to Mina, I just want to, because this is something that a lot of people say, well, I mean, there's a lot of myths about scaling up and scaling out. I've recently done a very complex and about 40-minute webinar on this topic. I invite you to go watch it on YouTube and our website. But I just picked 3 slides from there to show you what I mean by scaling up and out at the same time. So what I did here was a very simple experiment. I got, for those of you who are familiar with AWS, the first one over there, you can't, I think it's not very crisp and clear, but the first one in your left is the i3x large, it's a cluster of 3 nodes, and then I'm doing like quorum writes as fast as I can. It's an ETL kind of workload. I'm just ingesting data into the database, yes?
Is it the local storage?
Yes, that's local storage, yeah. But for writes, it doesn't matter that much. Because for writes, I mean, a lot of writes are in memory, etc. But we can talk about that later. It's not too much the subject of today's presentation. We tend to recommend local storage. But the first one is an i3x large. It has, I think, like 4 CPUs or something like that. And I ingest 1 billion rows in there and measure the time. And it takes around 12 hours. And then what I do is that I clear that cluster. And then what I do is instead of ingesting 1 billion rows, I'm now ingesting 2 billion rows. But I move my cluster to an i3 2x large. And it takes about the same time. And then what I do is that I move to a 4x large, and you got the drill, guys are all smart. So when I get you i3 16x large, that machine has 64 CPUs, 32 cores. I'm ingesting 16 billion rows about in the same time that I'm doing the other. So we scale up as well as we scale out. You don't have to run clusters with 310,000 nodes or etc. because being all small, you can consolidate them in fewer nodes. They're able to take your load. One example, of course, is their example. Their machines are pretty beefy. That's usually the way to go with Scylla, and you don't have to be maintaining 10,000 machines or something like that. What we hear after that is usually, oh, that's all fine and dandy, but good luck compacting that data, because now you're going to have like this latest data set had 4 terabytes of data. And our argument to that, if the database has the right architecture like we do, the disks are also getting faster. The CPUs are getting faster. You have more memory. Everything's scaling up as well. So we should be able to compact at the same rate. What's? Yeah, the network's a good point. But actually, the network is getting faster because the first ones, they have something like a gigabit network, and it's not even guaranteed. The last one is 25 gigabits. But you're right, the network is the only thing that doesn't usually scale that well. On the other hand, that's not usually where the bottleneck is. Most of the time, the bottleneck is disk and CPU. If you have a network bottleneck, it's a different story. I do recommend you get a 40 gigabit card, though. Have you seen them? It's absolutely amazing. Yeah. Yeah. So here's the result with compaction. So the first data set is around 300 gigabytes of data. The second one, 4.8 terabytes of data. So you're going to see is that we're doubling every time, doubling everything, data sizes, resources. It's pretty much constant. Oh, but then I'm going to lose a node, and I'm going to have to, and that's where your point is kind of true. But on the other hand, if you see Cassandra bottlenecking the network on streaming to a new node, you come talk to me because I haven't seen it. And for the record, I haven't seen Scylla do that either. The bottleneck is usually somewhere else. And if we were to, just think about that, if we were to bottleneck the network on a 5 terabyte data set, how long would it take to bootstrap a node? Half an hour. It doesn't take half an hour. It's usually for Cassandra, like, oh, it takes a day. What we see for Scylla is that they all took around 6 hours. All of them, regardless of the machine size. So if you lose a node, that's fine. If you lose a small node, it takes the same amount of time to recover as it takes to recover a big node. Provided, of course, everything is proportional. If you have around the same amount of data per core, data per CPU, data per amount of memory, everything works just fine. So Scylla scale up as well as it scales out. Yeah.
But this is assuming your network is faster for bigger.
That's exactly what he asked. I mean, but yes and no, because usually the network is not the bottleneck, right? He gets a plushie as well. Come on. If he has one, he gets another and give it to somebody else. By the way, about the plushies, just one comment. Some people write to us and say, hey, my kids love that plushie. If you have a story like that, you can also tweet us a picture, send us that. We love to hear that. But if you're like one of those people that say, my dog loved the plushes, please don't tell me. I don't want to know about it. And we've heard that in the past. So without further ado, I would like to get the stage for Mina. A round of applause, please. And I'll be back to tell you about the how later.
Thanks, everyone. So my name is Mina, and I am the customer use case today. I recognize a lot of faces. It's not my first time presenting here, and I feel like I bring AdGear here with like a report card every year. Like, look what we're doing. If you haven't heard about AdGear, it's a quick summary. So we're in the ad tech industry, so advertising technology. I'm going to try not to sound evil with all of the news regarding ad tech. We're really, really cool guys, and we do cool things. The company was started about 10 years ago. And when we started, we built our first product. It was called AdGear Console, and it catered to kind of two use cases: publishers who build websites and advertisers who show ads on those websites. Back then, that handshake to show the ads was a manual handshake. They'd call each other, they'd email each other. And so back there, when we said we did big data, really our infrastructure was doing between 250. There's no K there. That's like just doing 250. On a busy day, up to 5K a second, ads per second. 10 years ago, it's still something. It was something to be proud of. And then after a few years, we got into a different mode of doing advertising. It's called RTB, stands for real-time bidding. And RTB is essentially the same thing as before, but we give it different names. Instead of saying you're a publisher and you're an advertiser, we're going to call you a buyer, we're going to call the other guy a seller. And that handshake is no longer manual, so it's computers yelling at each other really, really fast to try to reach a deal in real time for the opportunities that are available on the internet. And then we kept saying, hey, we're doing big data. But over time, if you look at the graph of our volume, we're doing just a bit over 1 million of those transactions per second right now. And the next part of the story is we got acquired 2 years ago by Samsung Visual Display as part of growing something new called Samsung Ads. So there's us, and then there are some counterparts in other parts of Samsung. Altogether, Samsung Ads. So Samsung is a classical hardware manufacturer, but there are some unique data and unique big data opportunities acquiring us and kind of gluing it together with the other data sets that they have. Before I can explain what the cool part is tech-wise, I need to kind of take a detour and elaborate a bit on this RTB ecosystem, real-time bidding. So you as consumers on the internet, you're on the left side. And so you use some device, and it could be anything. It could be a mobile phone, a desktop, an iPad, even a TV. And the publisher who has managed this thing wants to make a little bit of money, and so they kind of put a frame that, I'm sorry, it's a little bit blurry. They kind of put this yellow frame where an ad needs to be filled. Now, because they have not done a manual handshake with an advertiser, that fulfillment is going to happen dynamically, which means as you visit the website has outsourced the fulfillment of this ad to something called an ad exchange. An ad exchange is an auction house, and so it receives this request, and it real time tries to find a buyer among many who is interested in filling that slot with an advertisement. And so you kind of see AdGear here. So we are a buyer. We listen to those arrows from multiple exchanges, actually. And in real time, along with our competitors, so those anonymous blue boxes, blue circles, everyone kind of looks at the orders in their system. Now, on the right side are our customers. So these are the people who pay us money. And they log into our system, and they put in orders. And those advertisers, those customers, put in orders with certain characteristics. And so, for example, we can have an order that says, hey, I want to show an ad to people who recently bought this specific jacket. I want to show an ad to people who are currently browsing a cycling website. I want to show an ad to people where I'm promoting a concert coming up. So if you think about the data needed to satisfy those different orders, they're varying. Some depend on the user, some depend on the time, some depend on what website, some depend on the application. And so our platform is essentially this. We take all of those arrows on the left side, coming in, like I said, at about 1 million per second. And then for each one of those, we evaluate all of the open orders in our system. And We are hiring. If you like optimizing this type of thing, it's, you end up essentially you're multiplying left by right, and you want to optimize that to be as fast as possible. Why do we need to do this as fast as possible? Is because, remember, the user is waiting for an ad to pop up there. And so the exchange, actually, when it talks to our server and to our competitors, there is a soft limit, and it varies anywhere from like 40 milliseconds to 120 milliseconds with the very generous exchanges. And so in that time, we need to receive the request, we need to parse it, we need to check all of the internal microservices that help us decide, we need to evaluate the targeting criteria. These are simplified targeting criteria. Sometimes each line order has multiple criteria that needs to be evaluated. Come up with the short list of who matches their targeting, see who's busted their budget yet, all of that stuff, and then finally respond. And all of that, we have to get our answer back to the exchange in a very, very short amount of time. And that includes transit time as well, so networking counts. So how do we differentiate ourselves from the other blue anonymous circles? A lot of it comes down to data. If you think of us as interested in buying something in the stock market, different people evaluate different securities different way, and information asymmetry plays a big part into how profitable you can be. So I'll give you an example. Back to the left side, we saw the user is on some cycling website. We might know in our database that this guy is Bob using whatever mechanism, by cookie, by some identifier on a mobile device, maybe even broaden it a bit to IP addressing. So we know that this guy is Bob, and in our database in real time that we're querying, we know a couple of things about Bob that help us distill the value of this opportunity that we're looking at. And so we value it differently than someone else with poor quality data. So we might know that Bob has previously purchased a very expensive bike, and we might also know that he habitually on TV watches cycling races, for example. Yeah.
Is this facts or provisions? I mean, did Bob really, the device of Bob, really purchase the $4,000 bike, or people with activities similar to Bob did that? And so
it might be a mix of both. So these might be facts about Bob, or it might be the result of data analysis. We call that lookalike, where we think Bob looks like some others. So the quality of the facts can differ. Yeah.
I'm just wondering, what is the proportion of ads you're serving now? Is it 20% of all the Samsung ads, or can you get an idea?
I don't think I can actually get into these numbers. So I can tell you that we are the execution arm for Samsung ads. So they're not necessarily using our platform to advertise Samsung products. They're using our platform as the execution model. So they turn around and sell that offering to clients.
Okay. And my next question is, since the integration from Samsung, so what is the Samsung culture about data?
Yeah.
Is that a great data culture? Can you describe that?
It's so part of the acquisition is Samsung actually realized they have a lot of data, and we have a lot of data and operational experience. So I think that's where the marriage kind of makes sense. And obviously, since the acquisition, more and more of what we build is tailored towards narrowing down that vision and what we're building forward to match what we want Samsung ads to look like. What kind of customers do we want to attract to sell the overall, the holistic product to?
Okay, thanks.
Yeah. So I just want to highlight, we consider this, for example, if these are facts that this is very good quality, it helps us value that opportunity in a nice way. Others might have lesser quality data, and others, when they ask their database, what do I know about Bob, they get a database timeout. So it really makes a big difference as to the quality of the data and the technology behind it. So that database on the right side, what do we need it to be? Well, we need to know as quickly as possible, what do we know about Bob? So essentially, it's a key to values store. It needs to be low latency. The database is not the only thing that helps us decide. It's one of many. And so it cannot take a long time to answer, especially if other processing within the lifecycle of that request depends on the answer from the database. It needs to be high throughput. So as we grow, we listen to more exchanges. Each exchange sends us more volume, we're buying more, so we need the database to keep up, which means it needs to be horizontally scalable. Yeah.
Can you shard an application side, like have a small silos?
You could, but
Here's a defect. Only one shard is down.
Yeah, absolutely. Yeah, yeah. And generally, we found that databases tend to be like that. So if there is a small shard outage, it doesn't affect the whole business. Like some percentage of the users don't get matched temporarily, type of thing. Multi-UDC by design, and the reason is we kind of move traffic across data centers in a slightly fluid fashion. So when a data center goes down, traffic automatically goes back to another data center, which means when we learn that Bob just bought a bike, and that's a write to the database, and then later we see Bob in another data center, we want to make that fact actionable. So it has to be by design multi-DC. Has to behave well under, yeah.
So what kind of, or how complex you can make an action? Is it really like check one thing, or you could check many things and then make some basic algorithm out of it?
How complex can we make the action to satisfy one order?
Yeah.
So we actually support, for our advanced customers, there's actually a mini language that gets evaluated. And so you've got groupings, ands, ors, whatever. Yeah.
It's a Boolean expression.
Okay.
Yeah. In our product, we give a simplified interface. So a lot of customers just say, show this ad to people in Canada, for example. Sure, we'll give you a nice UI widget that says in Canada. But for the more advanced customers, yeah, we give them a very expressive language to express what they want to target. Yeah. And it has to behave well under mixed concurrent workloads. So we've got this massive read volume needed for evaluation. We've got slightly lower write volume, so as we learn those facts, as well as sometimes those facts come in as a result of bulk data. So all of that happens in the same database, and we cannot sacrifice read latency to do these other two write types. So, yes, question? Yes?
Oh, yeah, I just wanted to know if there's an internal queuing system like Redis in Scylla.
Sorry, an internal what system?
Queuing, like outside.
An internal queuing system.
Yeah.
Yeah, it does. I mean, yeah, I'm sure. But I'm sure Glauber is going to be able to elaborate on that, right? Yeah, he's going to hop in with the gnarly details right after my piece. Yeah.
I'm just wondering, I think 2 years ago, someone from AdGear came and you were showing this video leveraging, I think it was HP Vertical. So
That was me, yes.
that was you. So have you, what's happening with this? I mean, are you stopping this and now you
No, absolutely not. So I'm still a fan of HP Vertica. HP sold Vertica to another company called Micro Focus. So I'm a fan of Micro Focus Vertica. We still use it. They are completely different use cases. So the use case here is, I know what do I know about Bob? Give me Bob's record as fast as you can. Vertica is more of a BI solution. So how many impressions did I serve in the last 3 hours? Give me an aggregate as fast as we can, as you can. We still run both.
Michael, catch it for a question.
Yeah. Okay, so 2010, we started using Cassandra. That was in version 0.6, and that was on Java 1.6. And it did the job okay, but my God, those were painful days. The software was kind of young, and even as our volume was not that high back then, but honestly, it was really painful. But things improved over time. Cassandra improved, and our company also grew. So it was really welcome to see, some of the things that were painful for us kind of disappear through features, through stability, things stabilize over time. So Cassandra, for example, initially, they kind of followed the Dynamo paper from Amazon, but they decided, hey, we don't need V tokens. Really, really painful decision. So they introduced V tokens. Yay. The way they store the tables and then they compact them had some weird timing issues and had some weird sizing issues. So you'd end up with some files on this that get really, really big, and then the new ones become small. So they introduced the LevelDB-like compaction strategies to kind of give you upper bounds on how deep the tree is at query time. Yay. They started realizing that some of the things done in Elasticsearch are really cool, which is if you have data and your GC is going over it because of the Java heap, hey, let's move that out of the Java heap. Nice improvements there. And then finally they said, okay, G1 GC, let's make that the default. Some pretty good improvements there. It's also easier to manage. Some of the tuning points for the JVM went away, but not all. And then there was a pretty hard fork where, Cassandra, as most people know, it's open source, and then the enterprise version, there was like a fork in the road, and that was slightly less impressive. Yeah. Now, around the same time this happened, it was last year, and we found ourselves at a tipping point. And on the left side here are some actual pain points that we were going through. So we're slowly losing the latency battle. Our volume grew, and of course, we would grow the cluster at the same time, but just the response time was slowly getting worse. It also hardware-wise, started to be the density and the value we extract out of each server was kind of getting worse. So we'd add more and more nodes, and nodes are not cheap. So we ended up with growing the Cassandra cluster without like a linear relationship to our business growth and the other stuff happening. And honestly, one of the nails in the coffin was not something related to Cassandra, but I firmly believe that we actually found some bug in the JVM induced by our load, and we just did not have the depth to to debug that kind of issue. For the most part, we're not a Java shop. And so, we started looking around, look at enterprise versions, but my realization was, after speaking to some people, that the enterprise version is just an enterprise package version of this, and as a technical guy, I did not see that as a solution. So what do? What are the alternatives? We started looking around. We started hearing a little bit about ScyllaDB. There was some outreach from Scylla as well as us reaching out. And what was really cool is the discussion that they were willing to have was purely on the technical side. What's your use case? Let's do a POC, no sales pressure. So I enjoyed that. So let's just focus on the problem of we need a database that does X, Y, and Z, as I've highlighted in the past. And the marketing was kind of cool. I saw ads online where you're supposed to do a service Cassandra stops, service ScyllaDB start. It's supposed to read the files as is, gives you the same endpoint, same protocol for the clients. So that was kind of cool. So we went through with a POC. These are some high level. Yeah.
What are the difficulties you face? Like you must be having some legacy data.
Yeah.
Like when you were switching from Cassandra to ScyllaDB. So what are the challenges you face in migration?
Yeah. So I'll tell you, regarding the marketing of like stop Cassandra, start Scylla for it to read the data, that was not very interesting to me. So what we've done is we've started a second cluster, and then we've modified our software to do double writes. So we started populating the new POC cluster. Then we modified the software to do double reads, and that gave us a true AA, not AB, AA measurements. At the same time, we talked to both, and so our graphs were showing how things are on both at the same time, exact same workload. Yeah, and we'll get into some of that. This is a high-level summary. Near the end, when we were switching, you can see that Scylla is roughly half the number of servers that we needed to satisfy the workload. The read latency, what we really care about, is a significant drop. And backlog and timeout, so these are internal metrics in our software. For the most part, they're eliminated. This is during the POC, so in 2017. It's worth highlighting. So there are two things on the right, Marina and Marina 2. Marina 2 is the Scylla cluster. The POC for a while was undersized. So it's worth highlighting that not only was Scylla outperforming, lower timing is better, it was outperforming Cassandra, but it was doing it with an undersized cluster, even for Scylla. So we ended up adding more nodes to Scylla until we almost flattened that line, and I'll show you what it looks like today. This is timing, and then this is timeouts. So internally, because we care about latency, we have to get back to the exchange with an answer right away. If the database is too slow, forget it. Let's move on. Consider that a timeout in the software. And so you can see we have a very low number of timeouts, and we almost ended up eliminating this after proper sizing going to prod. This is what timing looks like nowadays. This is recent, so we've gone to prod. And you can see we generally fluctuate between this 7-day view, so we'll go from 1 second at night when things are quiet to maybe 4.5, millisecond to 4.5 milliseconds when things get a little bit crazy.
That's one data center?
No, this is global across the 3 data centers.
That's global, and it's P95.
Yeah, it's P95 timing measurements. This is something very, very recent. So I just want to highlight this, and then I'm almost done. This was actually a recent change today. Our backend, the bulk of the backend that actually talks to that database is written in Erlang. some pros and cons, but some of the cons is that we did not have a well-tested client. So some of the optimizations that Glauber has been talking about, those tend to happen in the Java space, and it's just not a drop-in replacement. So we've been maintaining our own client, and that drop you see in timing on the left side today, it drops in one data center from 3.5 milliseconds to 2 milliseconds, is because we introduced what's called, in the client, a little bit of smarts, where it does something called token-aware routing. So instead of the client firing the read to any random node, it tries to send it to the node that it thinks owns that data, sharding-wise. And so that eliminates a proxy read by that node to another node, and you can immediate effect. So there is room for improvement given what we have.
So that was made in the code, or it's a configuration?
That was a code feature that LP here did, and we deployed to production slowly.
Most
and
modern clients already ship that, but they have their own client, or they didn't have that already.
Okay.
Yeah.
Okay, but normally it's provided by ScyllaDB.
No, it's provided by the client. Oh, actually, it's a good question. I'll talk about clients when I go to the stage again.
Cassandra client does the same. So if you happen to use an established Cassandra client against Scylla, your performance would start off at that lower level, because it has that feature built in. It just took us a while to add it to our client.
Mina?
Yes.
There is only ScyllaDB. You can compare with Cassandra. Do you consider other alternative too?
Do I consider?
Than ScyllaDB?
Sorry, I missed the last part of the question. Do you
consider other alternatives than ScyllaDB to Cassandra?
When you look at our criteria, no, we only looked at between Cassandra and Scylla. When you look at things we need, data center, replication, async, things like that, no, we evaluated Scylla and things looked good, and we went to prod shortly after. Okay, so honestly, I want to pass it on to Glauber at this point. So how Scylla does these things, I think are really interesting. I have not seen the rest of his presentation, so I'm looking forward to it as well.
Thanks, Trey. So before I actually go into the schedule presentation, I would just like to address 2 points that I saw that ended up popping out. The first point is about how we behave as a company, not only as a database product. And what happened with Mina and his experience really isn't an exception. That's how we like to do business. Like, we are all very technical people. Most of our team are just former Linux kernel engineers like myself. I mean, and we believe that this is the way to go. So we try to engage with people in a very deep technical level. That hasn't stopped, by the way, once they sign the contract. We still interact with them on hopefully not on a daily basis, sometimes on a daily basis. And the other question that was about clients, and a lot of people ask us that, I mean, how are the ScyllaDB clients compatible with, and then I'll stop you right there, because that's a new post question. There is no ScyllaDB clients. There's not. There's no drivers for ScyllaDB, because, as I said, we are fully compatible with Cassandra. So what there is there's the Cassandra drivers. And seriously, like, we try to, when we engage with people in POCs, we try to recommend changes based on what we saw, because we really like to do this deep technical interaction with you. But if you don't want to do any change, and just use the same code, that's what tends to happen. We don't ship drivers. We're considering maybe in the future to provide some optimizations and fork drivers. There are pros and cons without that. Probably we will. In their case, what happened is that they were not using one of the established Cassandra drivers. They were using their own in-house built driver. And that driver did not have token-aware routing, and now it does, and that's it. But if you use the Java driver, if you use the C++ driver, if you use the Python driver, probably they have that. Those that I mentioned, for sure they have, but there are other drivers out there, and that's it. I mean, we are really fully compatible to that point. What they did is also a very common thing to do. Like, although in practice we do say, well, we are compatible with the SSTable files as well, so we are compatible to that level. We don't recommend people migrating like that, because what they did is actually a very sensible thing. I mean, it's your data; it has value to you. So just do a POC, put them side by side, and migrate over. That's how most people end up migrating. With that address, I'll tell you a little bit about how we do those things. We've heard a lot from other people, from people that we engaged in the past. Oh, sure, we heard about your marketing material, but we didn't believe a word in it. So we didn't even consider Scylla because it's obviously just bogus. And I get it. I'm an engineer as well. So when I see people making, extraordinary claims, it's probably not true. I believe if I tell you how we do those things, you will get it that it is true. I mean, it's at least likely. You've seen that it's true from a customer presentation, but at least it's not like something completely out of the blue. I'll tell you a little bit about the design decisions that we make to get Scylla where it is. What you see here on your left side is how a usual threaded application behaves. So you have cores, you have CPUs. And then you have threads that are fighting to get to those CPUs. And to get to those CPUs, they need to do locking. And that is wasteful. That is super wasteful when they fight for control, and then you get context switches. And you haven't thought about that probably, but the cost of a context switch can get you around 10 microseconds, which is the cost of an I/O in a modern SSD. So every context switch that you did is an I/O that you didn't. And when we announced first Scylla, they were like, how can you get 10 times faster than Cassandra just by rewriting it in C++, which is how some people understood it should be. Yes, you're right, we couldn't if that was just what we did. I mean, get the Java code translated to C++. But what Scylla really is like an entire different architecture on the inside, keeping the outside the same. So what we do is actually the same thing that Cassandra does on the node level. On the node level, they do sharding. They get a token, and the token belongs to a node, and then if it doesn't route to the right node, I'll route it with token-aware driver. You can actually route to the right place. And we do the same with CPUs. A request belongs to a CPU. It doesn't belong to a node. So when we get the request, it's there. End of story. I'm not going to have any locking, because that CPU is the only one touching that request. That's it. So just out of the box, that's 80% of how we can get like the linear scalability that we get. If you run a system with 20 CPUs, you get X performance. If you get it with 40 CPUs, you get 2X. It's simple as that, just because of that. Yeah.
Do you enforce NIMA?
What?
Do you enforce NIMA?
Yes, very good question. Do you have a plushie? Get another, man. If you don't have it, it was the best question so far. This architecture tends to be very good for NUMA boxes. And why is that? Because not only the CPUs are sharded, the memory is sharded as well. If your box has a terabyte of memory, and you have 2 CPUs just to make the calculation simple, that's usually not what happens. It'll get you like half terabyte here, half terabyte there. The memory allocation, when Scylla starts, it just allocates all the memory in the machine, unless you tell us not to. If you leave it a reservation, we'll leave it a reservation. But if you don't tell us anything, we grab all the memory in the machine. We will identify which memory belongs where. So every memory access is NUMA local.
How do you do it on the cloud?
What?
How do you do it on the cloud when you sometimes don't have access to?
Oh, but the clouds are well behaved on that. What the clouds we usually do, I mean, before Scylla, we wrote the Xen Hypervisor, so we have a lot of expertise on that. And if you look at the hypervisor, it has all those features. You can do live migration, you can do this, you can export. None of the clouds actually do it, right? They tend to be very well behaved. So if they export you a view of the hardware, they tend not to do this crazy stuff about memory here and CPU there. If you look at Amazon, for instance, the way they sell you the instance is that you can have an instance with 2 CPUs, you can have it with 4, you can have it with 8. They're always in the same box, and if you buy one with 2 CPUs, it's here. If you buy one with 4 CPUs, it's there. So if the hardware lied to us, yeah, sure, we're gonna be paying the price for that, but that usually doesn't happen in practice. It's not a practical concern.
So in that kind of cloud mode, how sensitive it is to different machines? Well, it has to be exactly the same configuration.
No, we mean the cluster?
Yeah.
Oh yeah, but honestly, this is true for any distributed system. Running a heterogeneous cluster is not the best idea in the world. I've seen worse ideas though, but this is pretty much up there. So we do recommend you run like homogeneous clusters. For other reasons, it's not just this. I mean, in general, it's a good idea to have your cluster to be all the same thing. The second design decision that we make is that everything we do in Scylla is asynchronous. We don't use the reads and writes, the synchronous reads and writes API from the Linux kernel, by the way. Why? Because every time, and you got to remember that every time you do a context switch in a modern architecture, in modern hardware, that's one I/O that you haven't done. So you got to do asynchronous. Asynchronous also allows us to do batching. We recently, I published a report on the impact on Meltdown and Spectre on Scylla. And it was actually very minimum. The reason being, with our architecture, we are 95, 96% of the time in user space. When we have to do a system call, it's an asynchronous system call in which we batch a lot of requests together, send it to the kernel, and later on we go back and we don't take interrupts. We do busy polling. So when we look at all of those things together, asynchronous architecture is secret sauce number 2, because that allows you to get to speeds and hardware utilization. We recently bottlenecked the new i3 Metal, which is the machine on Amazon that is not virtualized that they recently announced. IO-wise, 10 gigabytes for writes, 15 gigabytes for reads, we can do it because our stack is extremely efficient. Close to the hardware. So we are in C++, and C++ really is, when we talk about C++ and we talk so much about that, it's not because the language is better, it's because it's a better gate to the underlying hardware. It's closer. It allows you to do this kind of things. We have our own memory allocator that we wrote, which is totally Newman chart aware. So that's why. So as long as the hardware doesn't lie to us, we know where everything is. We know where it belongs. We know where the CPUs are. We can do those things together. We don't lock the memory allocator. So if you do like a fully asynchronous architecture, but you use the operating system allocator, the glibc allocator, they will have locks. Now, by having our own memory allocator, we don't. The question over there?
Do you consider language like Rust to get less?
It's too, I think it's too immature. I mean, we did consider, but it's a nice language. I mean, I took a look at Rust in the past. I just don't think it's there yet. And like, we're here now, so we've got to find something that works now. And we also have our own disk I/O scheduler, which I will detail because it's one of the cornerstones of what we do. So we bypass completely the Linux scheduler. We just set it to NOP and none and whatever your disk exposes, and we do the scheduling. We have a CPU scheduler. So each of those threads, I'll just come back here, each of those shards, the puppy, they don't run like many threads. Remember what I said, a single context switch is an I/O that you haven't done. So we have a single thread. The Linux kernel doesn't get you out of the CPU. And in that thread, we have our scheduler that does all the scheduling. So that's how we can do the stuff that we do. We have our own cache. And that's why when we asked before, like, what about reads? I mean, Cassandra tends to be very good for writes, but reads are not there yet. One of the reasons is that if you have a Cassandra cluster and there's another thing that you have to tune, you have the Linux page cache for files, and then you have the key cache, and then you have the row cache, and then you have the key of the row cache, and then the row of the key cache. And how do you size each of those? And some of them are on heap, and some of them are off heap. And then you spend 4 months trying to figure out what the correct size is for all of them. In Scylla, as I said, we grab all your memory, we provide our own cache. When we do I/O, we don't do buffered I/O. We never go in, the Linux page cache is not in the picture at all. I forgot what my past 10 years were with mangling with the Linux page cache. God help me out. But it's no longer in the picture. We do our own caching. And one of the advantages of doing that is that we can actually do caching of parsed objects, not brute pages. So we can get very efficient when we go to disk. If Samsung Ads has, I want to go to disk and read 300 bytes. They actually can't because the minimum block size is 500 bytes, but so let's do that. I want to go to disk and read 1 kilobyte. The Linux page cache will only do 4K reads or paging. We go and we read 1 kilobyte because the Linux page cache is not in the picture. So you know your I/O gets more efficient. Everything you do gets more efficient. And as I said, we aim to be the autonomous NoSQL database, hassle-free, and we're getting better and better. We are, and I can tell you that for sure, we are already better than the competition in that, but we're getting better by the day, and I'll talk about some of the stuff that is really, really coming out of the oven like this week in the end of the presentation. We try to provide, a question over there?
Are you involved in Redis also?
If I what?
Are Redis, which share sister framework?
Oh yeah. So that was not really the topic here, but Scylla is written using something called the C-star framework, which is out of a coincidence was written by the same guys that wrote ScyllaDB a couple of months before they wrote ScyllaDB. So it might be because they wanted to write ScyllaDB. But other people have been using the C-star framework, which is, so a lot of the intelligence, a lot of those things like the CPU scheduler, the I/O scheduler, they're not actually in Scylla, they're in C-star, this framework that we wrote, it's open source, it's Apache. And some other people have been writing other applications, but we're not involved with that. I mean, we like that you do that, but our stuff is just to do Scylla.
Is it in any way meaningful to deploy this on Kubernetes? And there's some
Oh yeah, we recently had a webinar on how to do Scylla in Kubernetes, etc. So it's totally doable. You're not going to get as much performance as you're going to get from a bare metal or even virtual machine. That's not like how I usually recommend people to do it, but it's totally doable. We've been helping a lot of customers to do that as well.
What's the loss of the latency?
That depends, but one of the problems with Kubernetes is that it's not as no tuning as we would like, because you got to make sure the things are in the same machine. You got to make sure that, by the time if you don't do any of the tuning, it's you lose a lot. But when you do a little bit of meddling, you can get to 70% of what you would get otherwise. It's pretty good. It's still like databases are costly to run. So my recommendation is just go for the metal. We love that Amazon now released you can go and buy a box. You're not even virtualizing that anymore. But you can do Kubernetes. But coming back here, like we provide SLAs between requests and maintenance operations. So if you're going to do a repair, for instance, that's a pain point for a lot of people in Cassandra. I run a repair, my cluster die. I run a compaction, my cluster die. But with Scylla, because we have those schedulers, I'll tell you how, but this is why. Like because we have those schedulers, the IO scheduler, the CPU scheduler, the scheduler can tell, oh, you're a repair task. You're going to use 20% of the CPU, that's it, right? So I can guarantee SLAs between various tasks. Automatic tuning, automatic back pressure, scale up and down easily and fast. Why? We've seen the graphs. If you need to stream from a node, we're using all the hardware efficiently, not only to serve requests, but also to do those maintenance tasks. Question over there?
About scaling up and down, we talked about Kubernetes, but does Scylla provide any auto-scaling capabilities, like provision a new node, like ask?
We might be using the term auto differently, but if you're familiar with Cassandra, if you add a node to the cluster, it automatically joins the ring. But you still need to go there and add a node to the cluster. That doesn't happen automatically, yeah. And honestly, it shouldn't happen automatically, because it's not microservices. One of the things that people say, oh, microservices are great because you can just scale up and out and do everything automatically. Yes, but they are stateless. If you add a node to a cluster, there's 4 terabytes of data that are going to cross your network. You want to plan for that. There's a question over there?
Can you just stop that node in the customer's?
No, you cannot. So that's actually by design, and we're not compatible with the internode protocol. That's a mostly business decision, because if your node goes down, who do you call? So seriously, that's the reason. But and so we can do like ongoing repairs, because they can just be running on the background. They don't do repairs, which is a fine thing to do, but a lot of people do repairs, and you can just leave them running all the time, because you will have an SLA between those two things. And very complex data models that weren't possible with Cassandra, even though the language allows them, but they're just unworkable, become possible with Scylla because of the performance that we unleash. And now I'm going to,
Endless debate with Cassandra, which file system is better?
XFS. There's no debate with Scylla. And the reason for that is that we don't use the normal read-write mmap interfaces. We only use the asynchronous interface. And XFS is the least horrible file system for asynchronous I/O in Linux. Yeah. Now let's talk about throughput, because when we talk about performance, a lot of people are talking about throughput, right? Oh, I've done 1 million operations per second. Congratulations, pal. Everybody can do that. Like what I usually say is that, dude, Bruce Wayne can run as many operations per second as he wants, right? Because he has infinite money. He keeps adding nodes to the cluster, adding nodes to the cluster, adding nodes to the cluster, adding nodes to the cluster. You can do that with Oracle, for God's sake, right? Like it's going to cost you a lot, but throughput you can get throughput with money. Throughput is easy. Latency is hard. And what I'm going to tell you now is a story about latency. When we talk about latency, we don't want to, there is no number that I can tell you, this is my latency. That question doesn't make sense, because I need to ask you, which percentile latency, right? Latency is a curve, latency is not a number. In statistics and probabilities, distributions have many names. You got the normal distribution, you have all sorts of distributions. You guys are data science, I'm not. You know about that. But how do you call a distribution of latencies in which the higher percentiles, like the 99, the tail, is much higher than the average? How do you call that distribution? Any ideas? Whoever has an idea, get a plushie. Doesn't have to be a good idea, just get a plushie, man. Nobody remembers the name? Skewed? No.
Something about
Tail. I'll tell you. Well, maybe there are other names in the literature for that because you know naming is also hard as latency. But in Scylla, we call the distribution a bug. That's how we call it. And it shouldn't happen. And obviously, some workloads will naturally have higher percentile latencies. They're higher. For instance, if you're doing a read-heavy workload, some requests are coming from cache, some requests are coming from disk, of course. Yeah, this is going to be higher than that. But this should be determined by your hardware technology, not by the database. As far as the database goes, I want your latencies to be all the same. If it's not, and sometimes it's not because, let's be real, it's software. It's great software, but still software. It's a bug, and we'll fix it. To fix those bugs, I need to understand where those latencies coming from. And there are three main sources of latencies that I would like to talk about today. The first one being speed mismatch. Speed mismatch happens when you have one entity that is faster than the others. Those of you over 30 will remember that. And the slow guy will try to catch up with the fast one, but he just can't. It will be trying to do this forever, just can't. In practice, fast entity here, CPU's memory, slow entity disks. Things are changing. There are some disks these days that are crazy, but most of the time, disk is the slow. So what happens when those things are not in sync? And those of you who have done Cassandra in the past, you might have noticed this. Cassandra and other NoSQL databases as well, Mongo does the same thing. I mean, it's a normal thing to do. It's a normal thing for modern architectures. You're going to ACK requests from memory. You want to be fast, you want to ingest data very fast. So whenever I write you a memory table, I acknowledge that request. I write you a commit log. That's fine. But this request is not yet on disk. It's going to go to disk later. What happens with those things that are not in sync? Like, what if I keep ingesting? What if I keep ingesting? What if I keep ingesting? In some point in the future, I'll have to write that to disk, and I can't, and this whole thing is in memory. The queues get gigantic. Those things crash. And how do you handle that before ScyllaDB? Well, we're going to tune it. We're going to give more priority here. You're going to do more things there. You're going to, do something. I'm going to introduce something in front of my database to do caching and to serve as a buffer, something like that. And what we need to realize to understand that problem is that introducing latencies in that scenario is not a choice. It's not a choice because you're ingesting data much faster than you can actually write to disk, and you have to write to disk later. If you're not, it's like getting money from the bank. You're not going to pay them today. Someday, most people have to pay them later. If you are the bank, you don't have to, but most people do. But because the requests are very fast, later they won't be. I'm forced to do this. So if you look at this distribution here, this is ScyllaDB, by the way, but 2 years ago ScyllaDB, like our beta pre-GA ScyllaDB. The mean is not bad. If you look at this distribution, it's pretty cool. But when you look at the 99 percentile, it's like 1 second. Why? Because I had to stop to write stuff to disk. If I didn't stop, I would crash, which is actually what happens in some other databases. But let's stop and try to don't ingest requests anymore. This is part of back pressure. The 99 percentile is almost 2 seconds, and that happens actually to be the default write timeout. You're close to a timeout here. What we would like to do is spread those latencies over all percentiles. And if I have to introduce you latencies, I will, of course. The problem is specifying that, not me. But I want this to be smooth. And the disk slow, that happens. We call this problem the wall. Why do we call it the wall? It's because the requests are coming very fast, and then out of a sudden they behave as if they hit a brick wall. Happens with large payloads, slow disks, or a combination of both. So it's relevant in those scenarios. It's also relevant if you like Game of Thrones or you follow the American elections. It happens basically with mismatch between resources. Now, how do we solve that? As I said, we don't write, we don't read, we don't deal with the Linux page cache. So when we write stuff, we write to intermediate buffers internal to the database. And we know exactly the speed at which I can flush data from this buffer, because that's the speed that my pointer is moving, right? Because I'm doing through the device. There's no more buffering here. There's my buffer and there's the device. So if I wrote 2 megabytes in a second, that's because for whatever reason, that's how much I can write. Because there are other things happening, it doesn't matter. That's the speed that I can do. And so basically what we do is that we have a request queue, one for commit log, one for the memory tables. And if those buffers get full, what that means is that I can't do those things at the same speed. And then I stop the requests. But I don't stop until I get rid of the buffer. I stop until I flush a little bit of that buffer, just enough to get the next request in. Automatically, without any human intervention, what I did by doing this is I brought the system from memory speed to disk speed, dynamically. So that's ScyllaDB for you guys. If you look at the graph, this is just like one CPU, and we're zooming into that. The system starts very fast, but then that's what the disk can handle.
So basically, if you overload your system, the speed becomes the speed of the slowest clock.
Which is basically why you don't run heterogeneous cluster. Because in a well-designed system, they will run at the speed of the slowest component. But in Scylla, that happens automatically. And if we look at our latencies here, the median is much worse than it used to be. Like it used to be what, like 9 milliseconds? Say, oh, that's horrible. It got you 43 milliseconds. But that's actually good because now the higher percentiles, they're no longer 20 times higher than the average. They're just 4 or 6 times higher than the average. So we're very, very bounded. Why? Because the system dynamically responded to your workload. Second source of latencies is just lack of respect for limits. If you have a kid, you know what I'm talking about. So we understand that I mentioned we have our own CPU scheduler. And the way that worked in the past especially, is that Scylla is an IO-bound system. We designed the system to be IO-bound. Those tasks, those mini tasks that we're scheduling, moving from one task to the other is should be a simple function call. I mean, it's an event loop kind of thing. And I just move from one to the other. It's not very costly. And the idea is that those tasks will do something. They'll send a request to the network, and they'll move to the next task. Well, that's theory. But in practice, even on a database, even on a system that is IO-bound, you have some things that are pretty heavy on the CPU. You may be calculating a hash, you may be doing like a checksum, and more than that, you can end up with 10,000 tasks from compaction, and then if you order them in FIFO order like we used to, you kind of start getting latency problems because you have a lot of things that belong to the same entity queued in front of other things that they should be isolated. There is also a concept inside Scylla that we call the task quota or the poll period. And as I mentioned before, in Scylla, we don't do interrupts. We don't go to the operating system if we can avoid it. What we do is polling. Every X milliseconds, we go there and say, are there requests for me here? And we do this on a polling fashion. A lot of people, if you install Scylla and use Scylla, we're gonna use 100% of your CPU. Why? Because when I'm not doing requests, I'm polling. And then if I don't find any requests, yeah, but Amazon's paying the bill, man, come on. And if I don't see requests for a couple of milliseconds, then I go to sleep. But even a light workload can get you to 100% CPU because I'm doing polling. But when the system is actually busy with tasks, I'm doing this polling. And I need to go and do polling every 2 milliseconds, for instance. That's how our initial defaults used to be. Why? Because this polling is actually quite expensive. We've done a lot of work in the operating system even to get this to be cheaper. So we even have patches to the Linux kernel. You don't have to run a special kernel or anything. I mean, we play well with upstream to make those things cheaper. And our goal over time is to be able to do polling as fast as I can. Why is that? Because pre-2.0, before Scylla 2.0, our poll period was 2 milliseconds. If I have a poll period of 2 milliseconds, I'll never get you 1 millisecond under high utilization. Under low utilization, I'm polling, I can do much better than that, but I can't really get you like sub-millisecond latencies. Our poll period now already got you half a millisecond, and we want to go even further, right? So one of the things that is very important for latencies is to do this, to poll faster. And we've been doing a lot of work in the Linux kernel and in Scylla and in the libraries to be able to do this faster. But the other problem is the guy that just won't release the CPU. Like, as I call it here, the self-centered millennial teenager. You've all seen one of them. It's my CPU, and I won't yield. And what we've done in this situation is we merged something to Scylla called the block detector, which is just a very light thread that is running, and every, say, 10 milliseconds, however you configure it to be, I say I want to see anybody who is holding the CPU for more than 10 milliseconds, and then you set that to 10 milliseconds. Every 10 milliseconds, I'll go and I'll see if the task who is running is still the same task that was running 10 milliseconds ago. And if it is, I'll print a backtrace. Why a backtrace? Oh, backtrace looks like a bug. Yes, it is a bug, as I said, because we want to fix it. But it's a large computation that really takes 10 milliseconds. Then we will try to split it. We try to split it in small sizes. Why? Because I want to be able to preempt that task and say, now somebody else is going to run it. And that's how we get those latencies to be so low. So one of the solutions for that is to pull more often, and the other solution is what we fully merge now, what we call the CPU scheduler, which will actually define very specific shares. So you repair, you're going to use 20%, and if you have a large queue of stuff, I don't care. You get queued, I'll run the other stuff. The third source of latency is imperfect isolation. That happens, for instance, in The Walking Dead. If you have zombies trying to break into your house and your house is not properly isolated, I think you're going to have worse problems than latencies in that case, but in our case here, it's just latencies. Breakage of isolation happens exactly as I told you. If I have a large queue of stuff that it just has too many stuff, like a compaction. Compactions generate, it's the prime example that everybody uses. It generates a lot of work. If you don't control it, it will just use all of your resources. And Scylla, from the very start, from day one, we ship with what we call the I/O scheduler. And for the first year, that actually served us pretty well because most disks weren't that fast. So the disk is almost never your bottleneck. Your CPU is your CPU is usually not the bottleneck. Your disk's the bottleneck. And then if you control I/O, you end up controlling CPU. Why? Because those processes have a maximum parallelism. And then if requests don't come back fast enough, they won't go back to the CPU fast enough. So we never really bother too much into like CPU. We do now, because the landscape changed. As I said, I mean, Amazon has disks that can write 10 gigabytes a second, read 15 gigabytes a second. Intel has the Optane drive that we published an article about. Extremely fast 10 microsecond kind of latency devices. So the CPU sometimes is the culprit. But from the start, we have the I/O scheduler. What the I/O scheduler does is, when you install Scylla, the database runs a benchmark. So it's automatic. It's part of the setup phase. The benchmark will try to determine this that you see in the picture. What is that? If you look at a modern SSD, as you keep sending more requests in parallel, you get more and more throughput, right? You get more, they're fairly parallel, but there's a limit. There's this thing called physics. This is the enemy of any engineer. So I mean, I would like to keep sending requests and get all the throughput gets higher and higher and higher and higher. But unfortunately, there's physics, and I can't do this. I mean, the device has a limit. And if I send more, that's fine. The device will take it, but it will queue them. So what we would like to do instead is find this point at which this is it, man. This is the point in which the device can't take more. And if I have more requests to send than that, which I usually do, I'll queue them inside the database, not in the disk. And as I queue them, I'll tag them. You're a query, you're a compaction request, you're a commit log request, you're however you want to be. And, oh, but I have a queue of 10,000 commit log requests. Your query comes in to serve your bid. I don't care about the compaction request. The query is the next one to go, because the scheduler will enforce those quotas. We have that for I/O since the beginning, and we now, starting with Scylla 2.2, we have that for CPU as well. So we can actually run like extremely great machines, both CPU and I/O, perfectly isolated, and your latencies that come. Why does that introduce latency? Because if there is queue in the device and there is 50 milliseconds worth of queuing, even if I send you a new query request now, it's going to take at least 50 milliseconds. So I want that query to be 0. That's what I want. In practice, of course, that never happens. It's something like if I get you a millisecond, I'm perfectly happy with that. Right? Makes sense? So this is a major component, as I said, of Scylla since the very early version. Is a central component in how we solve the wall problem. Why? Because I mean, we can enforce priority just for the mem table writer, just for the commit log writer, and then if you can't write more than that, the system will auto-adapt, but the scheduler will tell you this is how much you gotta use, and it will prevent other things from stealing bandwidth from this writer. It's getting a major revamp for Scylla 2.3, which is probably due in 3-4 months, but the I/O scheduler is being The foundation is the same, but we made a lot of improvements focused now on latencies and complex size distributions. It always worked very well if all your requests were the same size. It didn't work that well if our requests were with a very complex distribution of sizes. Now we will, so we're also working on that. But we're shipping now, as I said, the CPU scheduler that does about the same thing, but for CPU. In Scylla 2.0, we had an initial version that wasn't fully ready yet. AdGear's been using it. It's disabled by default for most scenarios because it just wasn't there yet. We were enabling by default in AWS in our AMI if you were using the i3 instances because it was really important because those disks are very fast. But most people aren't using that yet for Scylla. 2.2, which is the version, open source version that we're going to be shipping probably this week or next week, already has the full solution. It's enabled by default anywhere, isolate workloads very well. And if the scheduler tells you, you're going to use 20%, it's 20% another story, right? But that's the part I like the most. Because who came up with the number 20%? Was it God? No, right? So who said that compactions have to run at 20% of the speed of the disk? And who said that mem tables have to run at 10% of what? Who came up with those numbers? What we achieved before with Scylla was fairness. I can at least have upper bounds for those things. If I say like everybody gets 33%, everybody gets 32%, and at least things don't clash into each other. But it's not enough for us. We're the autonomous database. So we want to do more than that. We want to look at those priorities. We want to look at the compaction priority. We want to look, those are actually shares on priorities, but I want to look at queries. I want to look at mem table flushes. I want to look at the compactions. And I want to ask the question, what is the perfect number? What is the perfect proportion of runtime between those two things? What? For the traffic that you get. And dynamically, for the traffic that you get. You have a plushie already? Give your plushie to someone else. Get him a new plushie. Destroy it. Oh, come on. He's got no plushie now. Another plushie. Another plushie. Come on.
Where are you? Who wants it?
Smart guy over there.
Okay.
Yeah.
Good try at the back.
So those things sound a little bit exoteric because that's not usually something that you do in software. But it is something that we do in the real world, for God's sake. And why can we do this in software? One example that I love is your car cruise control. You set the cruise control to 100 kilometers an hour, and the car figures it out. We have industrial controllers all over that can do that. I mean, you set water tanks. If you have a background in hard engineering, you've probably seen those things. PID controllers and other kinds of controllers that can automatically adjust rates and ratios and do those things. Who said we can't do this in software? Of course we can. And we did it. We call those the Scylla controllers. And they work about the same as an actual industrial controller. In this example that I love, you have a water tank that you got to. What's your goal? It's like a dam. I don't care if it's too low. I don't care if it's too high. But I do care if it overflows. I mean, keep it between a minimum and a maximum, and try to juggle that. If I have too much water, open the dam a little bit. If I'm running out of water, keep it closed. People do this in the real world. We do this in Scylla as well. And here's an example. This is the CPU scheduler. And I'm using those examples focusing just in one CPU so you can see what's happening in this one CPU. The scheduler said, just because God said so, that mem table flushes, when you get data on disk and you got to flush it to the SS tables, they use 50% of the CPU. Fine, because it's better than not having isolation. But if your workload is such that you can do this very fast, for instance, because your disk is very fast, what you're going to see is the behavior as you see in the picture. When I have to flush, I will limit the damage, which is great. But the damage is still there. Why? Because if you look at what happens between the peaks, I wasn't flushing during that time. So what I could have done is spread that. And your latencies would get even better. Because I'm getting this work that needs to be done over time and say, okay, you're too fast. You could be slower. You're a background task. You don't have to do this fast. If I don't do it fast enough, I'm going to run into the wall problem. So I need to keep things just like the dam between a range. And that's what we did. If you look here, I have a system. It's a little bit hard to see because of the lighting. But this first one here to your bottom left is the CPU usage in that CPU. It's 100% all the time. And it's fine because the scheduler is guaranteeing that everybody only gets the priorities that we assign to. And then on the graph on the right, we have the output of the controller. The controller said, run this at 50% CPU. For this workload, that's what the controller automatically calculated. And what you have in the other graph here to the top right is the actual limit. If I hit the yellow line there, my system is going to have to start introducing latencies. Preferably, I would like not to hit it. But you know, I don't have to go faster than this. As long as I'm there, I'm fine. And then when you look at the actual new curve for the request per instance, instead of this, it's that, and you have both here so you can compare. This is before the controllers and this is after the controller. How much human effort was involved in getting this workload? Well, to design it, a lot. To run it, 0. You just fire, you just put it there, and it runs for you. The algorithm calculates everything. Oh, and how do we know your magic algorithm works? Well, because people have been doing this in the industry for years and years and years, in control system, in planes. Our CTO actually happens to come from the aerospace industry. Like, people have been doing this, and we're actually doing this as well. What are the results of that? If you look at latencies again for that workload, if you see the spikes, every spike that you've seen is something that is going to make your 99 percentile jump. So before, for the same workload, before controllers and after controllers, 99 percentile used to be 4 milliseconds, give or take, and now it's actually less than a millisecond. Why? Because it could spread that across the workload. Coming new in Scylla 2.2, this is going to be released this week. We actually finished. We've been working for this for a long time. Flushes are an actually relatively easy problem. Compactions are hell on earth to control, but we did it. This is the output of a system. Throughput in green. So it starts with a throughput that is somewhat higher than I can actually sustain, and it keeps increasing in yellow the amount of resources, in this case CPU, because it's a CPU workload, that compactions are assigned to. At the very end, it's using something like 14% of CPU, and you see that it stabilizes because your workload stabilizes, so your workloads tend to reach steady state conditions. What happens if my workload changes? Now I want to find that out, and so we run this experiment. What we did is that I'm trying to send the same amount of requests. You can see that the system is not actually able to, but I'm trying, but the requests are larger. They're 3 times the size. So what happens is that I have more data to compact. I have to give more CPU to compactions, and then it just happens. The system reaches a new equilibrium. Those are the latencies. Again, this is the point where you have this straight line. This is the point in which the workload changed. My 99.9% millisecond latency used to be around 2 milliseconds. Is actually now just a tad little bit higher. My 99% got a little bit higher, and then my 95 is about the same throughout the workload. LP.
What's the time scale?
That's not days. I mean, this is just an experiment we wrote for an article.
I'm wondering what's kind of the frequency of the controllers.
The controllers run, it depends. The mem table flush controller run every 50 milliseconds because it's a faster kind of event, and the compaction controller runs every 250 milliseconds. So what they're going to do, after that window, they're going to look at what we call the backlog, and they're going to make adjustments. So say, okay, I flushed too fast, and so in the next period, I'm going to flush a little bit slower. Over time, this thing is going to be smooth. That's one of the things I'm dying to get into your system, man. Because that's going to do what I promise you. You're going to get your timeouts to actually 0, I'm hoping. They're coming soon. 2.2, we are controlling the size tier compaction strategy fully, which is the default compaction strategy most people use and everybody should use. And, and in 2.3, all compaction strategies will be controlled, the level compaction strategy, time window compaction strategy, and all of that. We also want to do that for repair, so you can, if you do a great repair, like a big repair, we'll figure out how much data you actually have to repair and try to adjust that automatically. So the summary, Scylla inherits the user visible architecture of Cassandra that we've seen over the years that was a winning architecture. It's known to scale out very well. Actually, I have a mistake here. It is known to scale out very well, but we employ a radically different architecture internally, allowing us to scale up as well as out, while keeping our latencies extremely low and predictable. We do that also reducing our TCO across the board by also minimizing our operational expenses. There's not a lot of maintenance that go with Scylla, and that's it. That's the Scylla story. I'll take more questions. Sorry.
What kind of overhead do you have for long memory or table?
What kind of what?
Of memory overhead.
Oh yeah, that's actually a good question because do you have a plushie? Plushie over there. That's a good question because when you have the overhead is not very big, but because we are sharper core, I can have data for a table that is in many CPUs, right? So I have to replicate that metadata in many CPUs. The overhead is not great, it's not big. We don't recommend, there's a magic number of tables that people usually recommend for Cassandra. We've seen some of our Scylla customers do a lot more. We've seen people using 1,000 tables. Do I recommend you do that? No, but if your workload requires you to do that, you can probably do that with Scylla just fine. I've seen 1,000, I've never seen more than that. Doesn't mean we could, I mean, it's metadata in the end of the day. I mean, it's not a lot. It's not gonna use like a gigabyte of memory to do that. The problems with many tables are actually not the memory usage. One thing to keep in mind is that they will be replicated across all CPUs. The problem with multi-column families is that the memory for mem tables are now smaller, right? So you had this one big giant piece of memory that I could use to buffer stuff and then write large SS table files that are very efficient to write. And now you have to split that in many smaller pieces. And the resulting SS tables, they're going to be much smaller, and you're going to have to do a bunch of F-syncs every SS table that you write. So that's why you lose performance. It's not because of the memory usage per table. Thanks.
Is it compatible with Cassandra? Like from
Yes.
metrics point of view?
Yes. Yes and no, because I don't like the JMX metrics. We have our own metric system. We export Prometheus natively. And all those graphs that you see here, they're actually from our open source monitoring interface. So we have our own monitoring interface. The reason monitoring is hard to simply be, let's just use their monitoring, is that monitoring is usually exporting data from the internals of the database. So if the internals of the database are different, the metrics are going to be different, and we have our own system for that. That said, again, Cassandra has JMX metrics. A lot of people already monitor Cassandra cluster with those JMX metrics. No, Graphite is the upper layer.
No, it's not sample GMX.
It is.
No,
It is. It is.
I was
Yeah.
saying over UDP without using any GMX crowd.
Well, the standard interface that I know from Cassandra is just you connect to JMX, you get an MBean, and then you grab an MBean from that. I don't know any other interface. That's the two interfaces that we support. We do the JMX. We don't recommend because you're not going to get the actual view of what's happening inside Scylla. And we have Prometheus, which are going to get you like a very good comprehensive view about what's going on inside the database. Over there.
I wrote 3% is clear that Scylla is basically optimized for performance, but then
You got a plushie as well, don't worry. Sorry.
is Cassandra the only alternative to ScyllaDB?
No, Cassandra is not an alternative to ScyllaDB. Nothing's an alternative to ScyllaDB, man. Come on. Who else has plushies?
You're saying you're an engineer, so I mean, when you do conversion, what you find? You're using Cassandra, you're using ScyllaDB, and what else are they comparing it to?
Yes, that's actually a great question. I'm just mocking because I couldn't miss the opportunity. But we always focus from the very beginning our go-to-market strategy in Cassandra deployments just because that's the easiest thing to do. But we have a lot of migrations from Aerospike. The reason people tend to migrate from Aerospike is that I wanted to run Cassandra in the first place. Cassandra just wasn't fast enough, but now Scylla is. But I never actually wanted to run Aerospike because Aerospike is a little bit weird. It does, I shouldn't say that, but you know, it's a great, I actually love Aerospike because the engineering stuff that they do is super impressive. And as an engineer, that put a lot of effort into this. I mean, you got to give them this. It's really great, but you got to keep your keys in memory, and then your data, your nodes start to get like super big, and it doesn't scale very well. So a lot of people doing Aerospike. If you want to do it, like if you really want to do the crazy latencies that Aerospike can do, and you're really looking at an in-memory database, you're not going to get latencies as good as that with Scylla generally, right? So there is a niche for that, but a lot of people doing Aerospike are just people who should be doing Cassandra, and they're not because Cassandra couldn't do it, and a lot of them are coming to Scylla now. We've seen migrations from Mongo. The usual thing that our customers tell us is that Mongo, it's really, as I said, this phrase that I said comes from a customer. Mongo is easy to start with, but as time goes, I mean, the curve really gets complex, and when we look at the Scylla curve, it's very predictable and linearly scalable. We've seen recently an ad tech company in France. They had Mongo and Hive doing two different parts of the pipeline because they couldn't find a database that could actually do those things, and they moved both to Scylla. Their use case in our website, Numberly. So we've seen a lot of, I was surprised by that actually, even though I have to admit that. I mean, I'm surprised how diverse our customers are, and the amount of verticals they're coming from, and the amount of previous databases they're coming from. It's still majority Cassandra, but it's not just Cassandra.
Do you have any benchmark comparison to Yugabyte?
No, but well, we seldom do comparisons. What we try to do is like we publish our numbers. That's it. We've done comparisons against Cassandra in the past, especially in the beginning. Yugabyte is a very interesting technology, not very mature. But they do one thing very well, which is like they do transactions. So that's great. But what you have to keep in mind when you do transactions is that you're paying something for that, right? So they're not really, their design, I've never actually run Yugabyte, but their design is not really an HA design. What they say is that we are a CPU system, but that's fine because your node's not going to go down anyway, which is true to an extent. Like, but for some workloads, you really want your cluster to be up at that point. So what they claim is like they're mostly HA. It's the same thing about the Google Spanner claims. Right? It's mostly HA, but sometimes it's not going to be. But we still believe that the HA design is the best design. Their latencies tend to get better for some workloads because they are CP, just as Mongo. You can query just one node. For here, if you want actual consistency, you got to do quorum. But on the other hand, your network's as fast. I mean, the numbers that they publish in terms of sheer throughput weren't very impressive, honestly, if you ask me. And I haven't run them myself. We haven't run comparisons. I do think the transaction stuff is cool. It's something that we might do in the future. We don't think there's, in terms of performance, I can tell you that it might sound biased, but I don't think there's a contender for Scylla these days.
Especially with the spanners. There is 5, 9 SLA, 6 SLA.
Yeah, but that's because you control the hardware, right?
How do you exactly compare with the OSLAs?
Well, I'm not Google, man. So that's it. I mean, Google is in a very unique position. The Spanner is actually nice. I mean, their transactions still are not that cheap. So the thing about Spanner is that they say, oh, we're SQL compatible. No, you're not. You're mostly, there's a lot of stuff that you can do, that you don't do with Spanner. And the transactions are still pretty expensive. I think they do like 7 network round trips to do a transaction. And when the thing is, you do those databases, you do transactions, specialize in transactions. When you need to do like the crazy high throughput with low latencies, you can't because you weren't designed for that, right? So I think honestly, I still think we are in a very good position to capture that market, like very high throughput, very low latency.
How about HBase?
HBase?
Last question.
Last question. So let's do another question.
We're all going to be at the bar afterwards.
Yeah,
so we can
over there.
I can talk with the biggest customer player like Netflix or not yet.
That's a business question. I can't answer you that. What I can tell you is that you have companies in Montreal that are using Scylla. I mean, we have many customers in the website. We have public use cases. There are some companies that are honestly very impressive. They're using Scylla. Can't disclose. Okay. Thank you.
Okay, last question.
Last question. Oh, you ask a lot. I mean, if you're really the only one I ask, but it's like we need some variety here. Yeah. With? Yeah. So yeah, like we optimize our database for SSDs because we do believe that it's 2018, guys. I mean, it's but that said, there is a very interesting use case that we're trying to bring to our enterprise release, which is tiered storage. Because some people do want to do like, oh, I have this piece of data that I do have to process very quickly, but then after a month I still want to store it, but maybe I'll access, maybe I won't. That we want to do, but it's not that you can't do, like Baidu, the Chinese company, they scaled the Scylla cluster to a petabyte using HDDs. They published that in the Scylla Summit last year. The videos are online.
What about the variance?
One?
Do you still get good variance, or do you still
Oh, it's harder because the disk, the disk technology is now imposing you a bottleneck, and not necessarily all this auto-tuning stuff is going to play very well. Use SSDs. I mean, they're becoming cheap enough. HDDs are still faster, but the only real use case that I still see for HDDs is really like the size, the tiered storage thing. And that's a use case that we do want to capture. We are in a good position because we can have like separate I/O schedulers, one using the SSD, one for the HDD. But still on HDD, I don't see a reason. It will run, but you shouldn't run. But it will. All right. Thanks. Thanks for having me here.